자, 그러면 텀 스트럭처에 대해서 얘기를 해보도록 하겠습니다. 텀 스트럭처라고 하면 무슨 말이냐면요. 보통 이자율이라 그러면 이자율이라는 게 단 하나만 있는 게 아니에요. 기간에 따라서도 이자율이 다르고 이자율을 제공하는 사람에 따라서도 다르거든요. 그런데 여기서는 이번 시간에는 이제 이자율은 다 무위험 이자율이고 대신에 이제 만기에 따라서만 이자가 변하는 그런 상황을 볼 겁니다. 만기에 따라서 이자율이 어떻게 변하는지를 나타내주는 이제 이론이 텀 스트럭처 이론이에요. 즉, 텀 스트럭처 만기 구조에 따라서 이자율이 어떻게 달라지는가를 나타낸 것이 바로 텀 스트럭처입니다. 그래서 이번에는 먼저 텀 스트럭처를 알기 위해서 우리가 알아야 되는 기본에 대해서 알 거고요. 그 다음에는 텀 스트럭처 이론들에 대해서 좀 더 깊게 들어갈 생각입니다. So in this class, we will first talk about the basics and mathematics of the term structure and the basic notations. 자, 그럼 노테이션을 먼저 볼게요. So we will use the following notations. So whenever I use the capital letters like P or Y or F, these are the nominal numbers. Whenever I use lower characters, these are log of P, log of Y, and log of F. So P T of N is the time T, price of N year maturity, 0 coupon bond. So you have time horizon like this. You're currently at time T, and when you are pricing a bond that matures N years after, N years after it's going to mature, so its payoff is going to be 1. And this price is going to be represented as like this. And log prices are very much easier to deal with in many cases, so we will use log prices many times. And the yield and the logs are related in this relationship. Okay, so yield of the annual bond is, say, can be like 1.05, okay? Or in a net number is 5%. And if you take the log of it, then you get the price and the year relationship like this. The log price has the following property. So if the log price of a 4-year bond is, say, -20, log prices are all negative numbers. It tends to be negative numbers. It means that it's on average at a 20% discount and 5-year yield or 5% yield per year. Okay, so log price has this good property that it represents the discount. Okay. So if the log price is, say, -20, then it means the bond is priced at 20% discount. Then the next important concept is the holding period return. Holding period return is defined in this way. So you buy a annual bond at time t, and you will sell it in the next year. Next year, time is t plus 1. Okay, so it's t plus 1 here. And when you sell it in the next year, the maturity becomes n minus 1. Okay, so the holding period return from t to t plus 1 is expressed in this way. Okay. And log holding period return is simply the difference in log prices. And in continuous time, holding period return can be represented in this way. So in the denominator, you have the price at time t. Now in the next period, let me draw the diagram. Maybe it's easier to understand. So time t, okay, and this is maturity. Okay. So maturity is date t. So this is when the bond matures. So when you sell it in the next period, say t plus delta, right? So when you sell it in the next period, time advances by delta t, but the maturity date is still the constant. You're selling the same bond, and we are expressing it as dp over p like this. But in many cases, it's easier to understand using fixed maturity bonds, right? So we are instead considering a situation where, so your time t and t, which is t plus n. So we're going to fix the time to maturity, right? So we are expressing holding period return in terms of the bond with fixed maturity. So you can express it in this way. So it's the first line is the same expression as before. So when you sell it in the next period, now the time to maturity decreases by delta t, and the time you sell it has advanced by delta t as well. Okay. Now we are subtracting and adding the same term. Okay. So when you do this, the first part, this one, okay, and the second part, yeah, let's take a look at the second part first, right? So the second part is basically keeping the maturity the same, the time to maturity the same. It is the change in the bond price in the next period, right? So this component is the return component, assuming that you're not selling the same bond, you are measuring the price change of the bond with the same maturity. So in other words, this bond and that bond are different bonds. These are different bonds. Okay. So this one, the first one here is you can think of it as time t to t plus n. Okay. So and t plus delta and t plus n plus delta. So the first bond, this one is basically this one. Okay. The bond that you buy at t plus 1, which matures at time t plus n plus delta. And the other bond is basically this, right? So why we are doing this way? Because it's easier to keep track of the bond price, the price of the same bond, instead of looking at, it's easier to keep track of the bond prices of the same maturities, right? So you look at the price of the 5-year maturity bond today, and also to look at the price, tomorrow's price of the 5-year maturity bond, instead of looking at tomorrow's price of 4-year and 364 days maturity bond. So you're not fixing the bond, instead you are fixing the maturity, so that you are comparing 5-year bond price, today's 5-year bond price with tomorrow's 5-year bond price, instead of comparing today's 5-year bond price with tomorrow's 4-year and 364 days maturity bond. So that is what is being done in this term. Okay. Now the first term here is basically correcting for this difference. Okay. Holding period return should correct for this difference. This is basically price change. So you are keeping the time at the same point, but changing the maturity, right? So it is basically comparing at the same time t plus delta, fix the time at t plus delta, and you're comparing two different bond prices, the one with 5-year and the other with 4-year and 364 days maturity bond. Okay, so that is the bond price change along the maturity. Okay, so that notation this decomposition of the holding period return into two components. One component driven by the price change of the 5-year bond, same maturity bond, I mean. The other component driven by the price change along the maturity curve. And the next important concept is forward rate. Forward rate is basically the rate you will lock in today for future loan. Okay, so say at time t, you are looking at n maturity and n plus 1 maturity rate. The forward rate is the rate that is known at time t, the rate of that will apply from t plus 1 to t plus n to t plus n plus 1. So that is the rate that you will lock in today for a future loan that will kick in from t plus n to t plus n plus 1. That forward rate is defined as the following. And the reason you can always derive it because you can invest $1 in two different ways. One way of investing $1 is you can use n plus 1 year loan, okay, for n plus 1 year. Alternatively, you can do n year with n year loan times, I'm sorry, there should be no times the forward rate that is going to apply from n to n plus 1. And because price and yields are related, and you can get the expression here. And also the other expression over there. And then forward rates are comfortable, very convenient when you calculate the prices because you can just, so the price of the bond today is basically the accumulation of all the forward rates. Okay. There's a typo, there should be ... Okay. So that is the forward rate. Forward rate can be defined in a continuous time. First, you define the instantaneous forward rate. So that is basically, you divide, so instantaneous forward rate is, okay. So you use the definition here, okay. So instantaneous forward is basically difference in the two log prices. Okay, so this is basically negative of p n plus l, or n plus 1 minus p of n over n plus 1 minus n. And as you shrink the difference, so you can change it to, you can change n plus 1 to n plus delta. Okay, so then it becomes p n plus delta minus p n. It's in approximation. In approximation. Okay, and then you get this instantaneous forward rate. So basically, forward rate is the derivative of pricings along the maturity curve. How the bond prices change over the maturity is basically the forward rate. Then what is good about the forward rate is forward rate describes the pricing of a bond. Okay. Forward rate can basically describe the pricing of a bond. Okay. In other words, like you see here, from the bottom two equations that log price is basically negative of integral of the forward rates, and you shift it into the bond prices instead of using log, then you get the last equation. Okay, then how forward rates and the yield curves are related. Because yields and prices are related, and we know that prices and forwards are related through the derivative we saw in the previous slide, we will plug in this expression for the yield instead of prices, and we get the second expression here. We can see this expression given here. Okay, and we can express it in the discrete time, and we get the following. The forward rate from time n to n plus 1 is basically your time n plus 1 yield plus the slope. So this is the slope, okay, of the yield curve. So the forward rate is going to be higher. So if you draw a time structure, this is time, and this is yield, and this is t plus n, and this is t plus n plus 1. Okay, so whether the yield curve here is upper sloping versus not, in other words, whether the yield at n plus 1 is here versus yield at year n, which one is greater? In other words, whether that is upper sloping versus downward sloping is determined by whether the forward rate from n to n plus 1 is greater than, okay, so if the forward rate is greater than the yield, then the yield curve is going to the slope upward. Whereas if the forward rate is lower than the yield, then the yield curve is going to be downward sloping. Okay. Now we will talk about the expectations hypothesis. So the expectations hypothesis is the classic theory for understanding the shape of the yield curve. In other words, if you look at the yield curve, okay, or the collection of the yields over maturities, okay, what does it tell us about the future yield expectations? Okay. So we want to understand about the future evolution of yields. We want to know what the future interest rate is going to be based on the shape of the yield curve. That is the purpose of the yield curve theory. Okay? And one theory for understanding the shape of the yield curve is the expectations hypothesis. In other words, expectations hypothesis is telling us that the shape of the yield curve tells us is the prediction of the future yields. Now, we have three identical statements of the expectations hypothesis. The first one is that the n-year yield curve is basically the average of the future interest rates. Okay. What it's saying is the following, right? The reason why, so let's assume that 1 year yield is 1%, but say 10-year yield is 5%, okay? So that yield curve is like upper sloping in this case. What that tells us about the future interest rate, according to the expectations hypothesis, is future expectation of the future 1-year rates. Look at this. These are all 1, meaning that these are all 1-year future interest rate. The expectation of the 1-year future rate is going to be greater than the current 1% rate. In other words, the upper sloping yield curve predicts that future interest rates, future short-term rates are going to be higher. That statement is basically the same as the second statement mathematically. You can show that later. What it's saying is basically the forward rate is an unbiased predictor, up to the, if you ignore the risk premium. Forward rate is the predictor for the future 1-year rate T years after. I'm sorry, N years after. In other words, the forward rate that's going to apply from N year after to N plus 1 year after is going to be the expected value of 1-year interest rate N years after. Okay? In other words, you see, as you saw in the previous slide, forward rate tells us about the shape of the yield curve. If the forward rate is higher, then it's going to be likely that yield curve is upward sloping. So what it's saying is that when the yield curve is upward sloping, future 1-year rate is going to be high as well. Now the third statement is basically holding period return of any maturity bond. Holding period return of a bond is going to be the same as short-term rate. Whether it's 5-year bond, 10-year bond, or 20-year bond, it doesn't matter. The returns are going to be the same as the short-term rate. And note that all 3 forms are the same. It is based on investor risk neutrality. Okay. In other words, what it's saying is that basically you can invest. So let's take a look at the first statement. You can invest for N-year period using the N-year yield. That's going to be the same as rolling over using 1-year rate for N-year period. Okay? But investors are risk averse. The two cannot be the same. Investors are risk averse, then the investor is going to prefer the N-year rate instead of rolling over using 1-year rate for N years. The next statement is the same. Forward rate is what you can lock in today. That is going to be the same as the future 1-year rate, only when investors are risk neutral. Third statement is also similar. Holding period return of all bonds across maturities are the same as the 1-year rate. When investors are risk averse, that cannot be true. Investors are risk averse, more likely that they will prefer short-term bonds over long-term bonds because long-term bonds are riskier. Therefore, long-term bond return should be higher. So so this slide summarized about what we talked about, expectations hypothesis. So the upper sloping curve implies that higher future short-term rates. You can understand that using one of the 3, especially the first statement in the previous slide. A 10-year long-term bond A 10-year long-term bond is not necessarily a better investment than 5-year short-term bond. What it's saying is basically whether you hold 10-year long-term bond or a 5-year long-term bond, according to the expectations hypothesis, the expected returns are the same. So 10-year bond is not necessarily a better investment. Okay. And if you look at the third statement directly, it says investors are risk neutral. Also, risk neutrality reflects a choice between the following 2. Has to provide the same expected returns. Okay, so in other words, whether you buy a N period bond or rolling over N period ND different one-year bonds. Okay? And you can also prove that the three forms are mathematically the same.